you so much. My computer has been freezing quite a bit frequently, and yesterday I had to shut it down unexpectedly, so I was closing down as much as possible so that it didn't freeze during your guys' class. Oh my goodness, so much creamer is used. All right, that's sad. We'll just leave it. I think there's still some coffee. Is the coffee gone or is it still there? It's gone. Okay. Eileen, when you get a chance, feel free to come up and grab the creamers, put them in, and then just kind of clean up there. Is that cool? Thanks, kid. Okay, section 9.1, sequences and series. Some of you, if you were helping friends in Algebra 2, maybe you already got a little bit of a review of this. There is one big term, I think one big vocab that's going to be somewhat new to you on this page. Can anybody find it? What's the new vocab word? I mean, for our pre-calc class, yeah, sequences. You did see them in Algebra 2, though. Discrete, yeah, discrete. If you guys notice, I said n is like x, right? Kind of in this chapter, n is like x. It stands for the nth term, as in a sub 1 could be renamed as the what term? The first term? The first term, second term, third term. Why is it called the nth term, or nerd term, or the first? Anyway, I'm done. Why is it called the nth term? Because after you get past the third, then what? Fourth, fifth, sixth, seventh, eighth, ninth, 10th, it's going to be a th for the end, right? Okay, so even though first, second, third, I know they're kind of weird as far as their little superscripts, but for the rest, it's going to be th, so therefore the nth term. But this would be renamed the what term? First term. Now, every now and then, n can actually start at 0. So we could call this the 0th term, or it could still be the first term, but when n equals 0. This could happen in something like, well, not specifically, but an example of why something might start at 0. Think physics if you're talking about a situation with motion, and you're talking about the beginning position. The beginning position might not be after 1 hour or 1 minute or 1 second has passed. It might be when 0 seconds, 0 minutes, 0 hours have passed. So that might be a time when 0 would be the beginning and not 1. But for sequences, almost always, at least for your guys' level, 1 is going to be the beginning. And so then the 1 would be the first, the 2 would be the second, 3 would be the third, etc. But what's this whole discrete word talking about? If n is like x, why is it weird that n would only be 1 and 2 and 3 and 4? Why would it be weird that n would only be 1 or 2 or 3 or 4? It's alphabet for you. Yesterday we had to write it on Post-its, or just putting it on their tests. Okay, discrete. So what's it mean? If we were to graph a sequence, we would have 1, we would have 2, we would have 3, we would have 4. Depending on what the terms are. Hold on, let's use these terms over here as an example, and I'll try to tie it all together. If you guys want, you can put this graph over here on this page, and I'll try to explain to you discrete after we talk about what the first 4 terms are of this sequence. So what's the first term? Why? Good job. What's the second term? Because? Third term. Pause, forget about the math. What's the pattern? What's the next term? How do I know that for sure? Why is it adding 3 every time? How does the math show us it's adding 3 every time? Not just with the answers. Because there are patterns that look to be one thing and all of a sudden they change. How does the math tell us it's adding 3 every time? Isn't 3 being multiplied by a higher number every time? And isn't multiplication just saying how many 3's we have? Right? Isn't multiplication just repeated addition? So 3 times 3 means 3 sets of 3's. 3 times 2 is 2 sets of 3's. 3 times 1 is 1 3. So every time, what are you doing? You're tacking on an additional 3. So plus 3 plus 3 plus 3 would be our pattern. For those of you guys that remember there are special names, this would be an arithmetic sequence. Arithmetic? Arithmetic? Anyway. But what was I talking about with the whole new term vocab of discrete function? What would I graph at n equals 1? n is like my x, a sub n then must be like my y. What would I graph at n equals 1? Yeah. What would I graph at n equals 2? Uh-huh. What would I graph at n equals 3? What would I graph at n equals 4? Why am I just putting it in a straight line? Aren't linear functions such that if you go over 1, you go up a constant amount? So go over 1, up 3, over 1, up 3, over 1, up 3. So it's going to look linear. But here's the struggle, guys, with sequences. What are we going to do? Because if it was x values, if it was y equals 3x minus 2, we would connect the dots because x is allowed to be 1.1 and 1.75 and 1. Everything in between. But a discrete function is such that only certain x values, even though they might be infinite, this sequence could go on forever and ever and ever and ever. It's still infinite, but it's a very different type of infinity. There are not infinite values in between. It's just at 2, at 3, at 4. Very different type of infinity. So with sequences, what I mean by discrete, you can think not connected. You can think not continuous. That might be another way of thinking about the word discrete. Not continuous. If it helps as far as remembering, you could think not connected. So if we were to ever graph a sequence, it's going to be separate dots because we just have a first term, a second term, a third term, not a 1.5 term, not a 2.213 term. Nope, those don't exist. Does that make sense, the whole idea of discrete? Only for certain values, not for the in-between values. But it makes sense. A first term, second term, third term, why would we need a 1.1765? We wouldn't. There would be nothing there. There would be nothing there. Okay, with that, let's get ready to keep going. Not continuous, not connected. Okay, so defining sequences. This is very much an intro section. This is very much an intro section. We might be able to finish it all today. Odds are we're going to finish almost everything and just have a little bit more to do tomorrow. Tomorrow is not another full day on section 9.1. It's just a little bit more 9.1 than 9.2. So the homework isn't due till Friday, but technically you should probably treat it as though it should be mostly done tomorrow. Defining sequences. Defining sequences. So instead of saying y equals, we're saying a sub n equals. A sequence can either be defined by a formula, just a sub n equals, or by the sequence itself without a formula. If you're just given a sequence by itself, that's great and all, but if you need to find more terms, you're going to have to identify a pattern. And a pattern that not just works for the first 2 terms or the first 3 terms, but will work for all the terms. But you can assume that the pattern will not change in the ... of what they show you. You can assume the pattern will not change in the ... that they show you. So if they show you the first 4 terms, make sure the first 4 terms work in the pattern that you choose. But you don't have to be stressing about the 5th term, maybe throwing it all off. So however many terms they give you, they've given you enough to find the pattern. And if they're giving you a sequence, and you're trying to come up with your own a sub n formula, which is arguably one of the hardest topics of the entire chapter, which shows up right here in 9.1. If you're trying to find an a sub n formula, you're trying to discover a relationship, not just as to how to jump from one term to the next, but also how to state how to jump directly to a term, not by going through the pattern, but by going directly to the nth position of where it is. Let me give you an example. What if I was to give you something like, let's do an easy one, 2, 4, 6, 8. Who do we appreciate? What if I was to ask you for the 7th term? Just a sub 7. $14? Some of you guys found a pattern and used that and jumped straight there. Others of you were trying to be like, wait, okay, so we have 4 already. So then 10 would be 5, 12 would be 6, 14 would be 7. Some of you were following the pattern, adding 2, adding 2, adding 2. Others of you were like, I think there's a pattern here. And for those of you that found a pattern, not just how to jump from one term to the next, plus 2, plus 2, plus 2, plus 2, but how to go to the 7th position. We're going to see if we can find a formula in just 1 second, but here's my question. What would be a sub 30? Now I'm basically giving an advantage to those that can jump ahead and don't have to go through the plus 2, plus 2, plus 2 process. What do you guys think? Okay, let's check it. Let's check it. What could be a formula, an a sub n formula that says, give me an n and I'll give you the term? What could be the formula? 2n. Good, 2n. Because the first term was just 2 times 1. The second term, 2 times 2. The third term, 2 times 3. The fourth term, 2 times 4, right? Now let me make it a little bit trickier, though. You ready? So wait, pause. 2 times 7 is 14. Were we right? Yeah. 2 times 30 is 60. Were we right? Yeah. What if I was to give you instead, though, 3, 5, 7, 9? Oh, this should be easy. All right, cool. What if I, not what I'm asking, but thank you. What if I was to ask for the 7th term? What if I was to ask for the 30th term? That's what he's saying. Let's see if he's right. What would the formula be? Now, these are very common ones, evens and odds, but that does not mean that they're easy. Some of you have seen these before, and they're probably the ones giving the fastest answers. Just a few that I've ever taught without ever having seen something similar could have come up with that quickly. Just a few that I've ever taught would have been able to come up with that quickly if they had never seen the idea of formulas for evens and odds before. So then coming back, this is not an easy idea, and some of you haven't seen formulas for evens or odds before, and so you're like, what? Doesn't mean that you couldn't have counted. 3, 5, 7, 9, okay, that's 4 terms. 11, 13, 15, 7 terms total. Would have landed at 15. David was right. He saw a pattern perhaps and said like, oh, hey, well, if 7 lands at 15, or if 4 lands at 9, or if 3 lands at 7, or if 4 lands at 5, isn't that just going to end up being 2 times double the number, the even number, plus 1? It's 1 above the even that you would get from this formula up here. So you could take the 2n, you could add 1. That's one way of doing it. Why wouldn't it just be like 3n or something like that? 3 times 1 is 3. 3 times 2 is 6, though. 3 times 3 is 9. Yeah, it's not even close. So I couldn't just multiply. What I need to say is, hey, let's take the evens, 2n, and either let's add 1 or let's subtract 1. What would the sequence look like if it was 2n minus 1 instead? What if the formula was 2n minus 1 instead? If I had started here, 2n minus 1, then 2 times 1 is 2, take away 1, I would end up at 1, 3, 5, 7, 9. What if I wanted you guys to get the sequence of 9, 11, 13, 15? Now what? What would a sub n equal? Two n plus 7? Would that work? What's n for the first term? 1. What's 2 times 1? 2. How much do I need to get to 9? 7. Okay. So then 2 times 2 would be 4. 4 plus 7. Oh. 2 times 3 would be 6. 6 plus 7. Oh. 2 times 4 would be 8. 8 plus 7. Oh. Yep, that'll work. Yeah? Okay. If you ever have patterns of even or odds, there are always ways of dealing, whether by multiplying even for evens or multiplying by an even and adding an odd for odds. Even and odds, even though they're kind of tricky, there are definitely formulas that help us know how to deal with evens and odds. But just a hint, those aren't the only types of sequences you'll ever see, right? What if you had something like this? Pause, no one say anything out loud. Shh. But feel free to start playing in your head or on paper with what the formula might be. It's a pattern once seen, easily understood, but sometimes quite difficult to come up with on your own. It's a pattern once seen, it's easily understood, but can be difficult to come up with on your own. So shush and don't say anything. You, yourself, and you. Can you find a formula such that when n equals 1 is plugged in would be 0? When n is 2 plugged in would be 3? When n is 3, when plugged in would be 8. N is 4 plugged in would be 15. N is 5 plugged in would be 24. Don't say anything. Someone who thinks they have the, don't tell me the formula. Someone who thinks they have the formula, what would a sub 13 be?
68.
What? 168. Yes, it would be 168. Pause. Use that as a clue. And no, he did not get that by actually getting all the way to 13 by adding odds. Some of you saw a pattern of +3, +5, +7, +9. You're right. But John did not get to a sub 13 by adding higher and higher and higher odds until he got to the 13th term. Someone else besides John who thinks they have a pattern, do not give me the formula. But what would be a sub 9? Yeah. Trying to give you more clues, seeing if that helps. Someone else who knows the pattern, do not give me the formula. What would be a sub 7? How many of you guys have the pattern? Give me a quick thumbs up. One squared is 1, take away 1. 2 squared is 4, take away 1. 3 squared is 9, take away 1. 4 squared is 16, take away 1. 5 squared is 25, take away 1. 7 squared is 49, take away 1. 9 squared is 81, take away 1. 13 squared is 169, take away 1. Struggle. But was it as easy as the even odd formulas? Not even that those were easy, but was it as easy? Not for most. How many other types of patterns could there be or formulas could there be? Tons. This one is an example of a sequence that has a pattern for sure. Not multiplication, but addition. +3, +5, +7. However, do you guys see the odd numbers reflected in that formula at all? I don't see a 2n + 1. I don't see a 2n - 7. I don't see a 2n. I don't even see a 2n at all. Even though the odd numbers were involved in the pattern, they're not involved in the nth term formula. And here we kind of come face to face with a dilemma that Algebra 2 kids faced and you guys will face in this very first section, but not really again. We're going to deal the majority of Chapter 9 with two special types of sequences, arithmetic and geometric. One has a constant difference, a set constant that's being added every single time, and then the other has a common ratio, a set constant that's going to be multiplied every single time. The reason why we don't go into all these other sequences is because beyond arithmetic and geometric, the formulas are kind of sky's the limit in the sense of there can be so many different types and so many different kinds. And making formulas for those nth term formulas can be very difficult, if not impossible. So we're going to deal with some of the most basic ones. Preparing actually in some ways for Calculus BC, in some ways, for Calculus BC where sequences and series come back. Not Calc AB, but Calc BC. Sequences and series come back. So once again, is it a helpful skill to be able to come up with these formulas on your own? Yes. Is it something that comes a lot more natural to some of you guys than to others? Definitely. So the nice thing is for the majority of Chapter 9, we'll be dealing with special types of sequences and series that have certain patterns that we'll capitalize on to get A sub n and even future, or and also S sub n formulas that we'll work with. So we're not going to necessarily have to have this skill completely down because some of your brains just think differently and that's okay. We're not going to have to necessarily make this connection for all of Chapter 9. Is that a good thing? Okay. Doesn't mean you won't have some fun, but Chapter 9, Section 1 is the only place where you're going to really be stretched as far as having these nasty sequences, not nasty, but complicated sequences whose formulas could be complicated. Here's an example, kiddos. How similar do these two sequences look? If they only gave you the first 3 terms, could you be in trouble? Because if they only give you the first 3 terms, maybe some of you would see this and maybe some of you wouldn't. This isn't just 2 times n, 2, 4, 6. This is 2 to the n, 2, 2 squared, 2 cubed. So that's one thing to notice. There's not a 6 in here. Some of you guys might have just done 1 over 2n. There should have been a 1/6, and there's not. It is 1 over 2 to the n, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th. But the problem is, if they just showed you the first 3 terms, couldn't it also have been this formula? 1 over 2, 1 over 4, 1 over 8, 1 over 15. What the? Want to come up with that one off the top of your head? No. Okay, hence why we're glad one more time that all of Chapter 9, the majority, actually every section past 9.1, is not going to give us these weird, funky formulas or sequences where we would have to come up with that term. Instead, they'll give us maybe, later on, they might give us this one and have us deal with it, but this is, to be honest, something that would be a little bit more complicated for future math, not for pre-cal. We'll be dealing with ones that are a little bit simpler like this one. Because this one, we could think of it as 1 over 2 to the n, or we could just think times 1/2 times 1/2 times 1/2 times L. It's geometric. Anyway, that was just a quick little be careful. Be careful. Even if you find a pattern that works, make sure it doesn't just work for the first 2 or the first 3. Make sure it works for whatever is shown. But as I said earlier, whatever they show you is enough to make sure you match it with the right formula. Does that make sense? Okay. Okie dokes. More basics about sequences. We talked about A sub n. It's a formula that says, give me n and I'll give you the term. We talked how there are patterns. And with the patterns, sometimes the patterns help us jump from one term to the next, but don't really help us with that whole nth term formula thing. We've talked about how A sub 1, A sub 2, A sub 3 denotes a certain placement in the sequence as far as the first, second, third, 5th, 10th position, whatever it may be. But now we're going to quickly touch on how there are 2 different ways to get formulas for these guys. One way is what you've already seen with the A sub n, but that's not the only way to do sequences because of a little thing called computers. If we didn't have computers, we would work really hard on having you guys get better and better at making those nth term formulas off the top of your head by yourselves. But we have computers that can do repeated tasks very quickly. Repeated tasks like, for instance, trying to find the 13th term and seeing the pattern of just adding the odds and being like, well, forget the A sub n formula. I'll just have a computer make the 13 jumps for me real fast, or the 100 jumps to me real fast, or the 50 jumps for me real fast. And the way of doing that would be a type of programming called recursive operations, or if we're trying to do it mathematically, recursive sequences. Carl? Well, let's just fill them in, then we'll see, huh? So, pros. If the recursive sequence is, in a sense, I know this is going to be very, very, very technical. My little way of talking about recursive sequence, or recursively defining sequence. Recursively defining sequences. There you go. It's the jumpity jump jump one. Jumpity jump jump. You're welcome. You're kidding? Okay, never mind. Anyway. What do I mean by jumpity jump jump? You're just jumping, 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 jumping. How? First term to the second term to the third term. To get to the 10th term, go from the 1st to the 10th. To get to the 20th term, from the 1st to the 20th. To get to the 50th, from the 1st to the 50th. Figure out the jumpity jump jump pattern. Figure out the how do I get to the next term, to the next term, to the next term, and then repeat. As a human, that could get really rough if we wanted to find the 100th term of something without having some sort of pattern or formula to solve. But can a computer repeat quite a few things very, very quickly? Oh, yeah. So therefore, the jumpity jump jump, the recursively defining sequences or recursive formulas for sequences, the pro is usually the recursive patterns are easy to spot. The recursive patterns are usually easier to see. The patterns are usually easier to see, like in that one that we just saw. If you had figured out it was +3, +5, +7, +9, you're like, fine. It'll take me a while, but I'll get to the 13th, even if you weren't able to come up with the formula. So that's the con, is that it might take longer to do, take longer by hand, right? A pro to the whole recursive sequencing is that it can be easy to program. It can be easy to program. Tell a computer, hey, repeat this over and over and over again, please. Whereas telling a computer to go find the nth term formula of a given sequence, unless it's one that's in its library, it might not necessarily come up with it. It's a lot easier to program. Con, you have to learn the programming language to do it. Okay, well that's fun. Now we're not going to go into Java or anything else today as far as different programming languages, C++. We're not going to go into programming. We're not going to go into coding. But what I'm trying to say is recursive formulas are harder to deal with even in your calculators. So if you guys have your calculators, go ahead and grab them out. The formulas look more complicated. I do need you guys, as you write the example down below, I do need you to go ahead and change. Here we go. I could change it either way. Not change, but kind of add to. I wasn't able to put in the little subscript that I wanted to. Put in a little k+1. That's nasty. Put a little k+1 over here. We could have also changed it to make this guy k-1 with the little subscript, but we'll just change it to be k+1 on the left-hand side. First of all, if you guys look at this little formula, it's harder than a sub n because, first of all, you have two pieces instead of one. That's kind of weird. A sub n, it's just like a sub n is equal to n squared minus 1. Cool, plug in n is 1, n is 2, n is 3, n is 4. This one, for some reason, they gave me two pieces instead of one. And second of all, if you guys notice, aren't there two different subscripts? So there's this guy that we're trying to find, and then there's this guy? What's going on? Let me show you just how the formulas work. A sub 1, well, we know that. That's going to be what term? The first term, right? 14. Okay. Now, question. According to my recursive formula, or recursively defined sequence, what would a sub 2 need to equal, and how will we find it? To get to a sub 2, it's going to be 1 more than a sub 1, which means we take a sub 1 and multiply by -2. A sub 2 would be -28. Someone who sees the pattern from the recursive formula, or even just from the step that we just did, what would the next term be? Positive or negative? Good. Because to get a sub 3, you would need to multiply to get a sub 3. He's 1 more than a sub 2. So you would take a sub 2 and multiply by negative 2. A sub 2 would be negative 28, which would be 56. So even though I'm plugging in numbers, technically we would say a sub 2 is equal to negative 2 a sub 1. That's how the formula works. A sub 3 is equal to negative 2 times a sub 2. So for instance, if I was to do something like I did a second ago with that 1 with the n squared minus 1, if I was to ask for the 13th term, recursive would just be able to say, I don't know, but if you knew the 12th, you would just multiply by negative 2. You're like, cool. The problem is you would need to know the 12th term, and to find the 12th term, I don't know what that is. Just multiply by negative. To get to the 13th, what do you have to get up to? You have to get up to the 12th and then make your jump to the 13th. So the pattern is easy. It's like, oh, just multiply by negative 2 over and over and over and over and over. But by hand, that could get really tedious, especially if they start asking for the 13th term, the 25th term, the 57th term, the 102nd term, the infinite term? Don't worry, that's the end of chapter 9. What is the most famous recursively defined sequence, possibly even without an nth term formula? Fibonacci. Anybody know the Fibonacci sequence? Oh, this is sad. Huh? It is that in some ways, shapes or form. Fibonacci sequence. Basically, I think originally it had to do, or at least it was illustrated with, reproduction of rabbits. That's kind of random. But it is seen in nature. It is one of the most commonly reoccurring, I wouldn't say numeric ratios because it's not a ratio, but it kind of has to do with one. It is naturally recurring in all sorts of things. Anything from the ways that flowers or buds bloom on a branch to the placement of seeds in a sunflower in the middle to the arrangement of the little knots on a pineapple to the spiral of a conch shell to, nope, those are fractals, sorry. Don't worry, this conch shell is still good. Just the next example I shouldn't say. I don't even know. There's like tons of them. To the perfect proportions of like an ideal face. If you study art, you could talk about when they were trying to do like perfect people versus like real people, and then there's a whole shift. But anyway, with the golden ratio. Fibonacci sequence. How would we define 1, 1, 2, 3, 5, 8, 13, 21, 34. What's the pattern? Add what, Andrew?
You add the previous term to the current term, so 1 plus 1 is 2, and 2, you add the previous term, which is 1, to get 3, and so on.
But here's the struggle. So to get a current term, you don't add the previous term. You add the previous 2 terms. So to get 2, you have to add 1 and 1. To get 3, you have to add 2 and 1. To get 5, you have to add 3 and 2. To get 8, you have to add 5 and 3, right? Why did someone point to that and say that's Fibonacci? I don't get it. They're just numbers. How is that Fibonacci? Because if you make a little 1 by 1, put on top of a little 1 by 1, area of 1, area of 1, but put those two together, and what's the next area? Making a square, it'd have to be a height of 2, so then 2 by 2 would end up being our size, which would have an area of 4. And if I was to keep on going, wouldn't now we have, I should probably show the measurements, the dimensions, you guys aren't tracking. I have a height of 1, a height of 1, and now I have a length of 2. And now I have a length of 1 plus 2 would be 3. And then I do 1 plus 1 is 2, and 2 plus 3 is 5. And then you do your 5, which would go up, right? And come all over here. So I'd have 5, I'd have 6, and I'd have 7, and I'd have ultimately 8. And if you guys follow the corners, nope, we're going to start at this corner. Follow the corners. Did I start the wrong quarter? I did. I always start the wrong one. There we go. Corner to corner to corner to corner to corner to corner. You would have the perfect spiral. So Fibonacci, it's not just numbers, and it's not just placements of different things, like what I was saying with the seeds and the pineapples and the conch shell. Well, the conch shells. These numbers can actually be seen in perfect spirals that are seen in all sorts of different things in nature. Anyway, one day we might go a little bit more into it. Vihart has some really great videos on it. But for right now, hold on, before we get to factorials, struggle. It's recursive. How do you jump to a place in the Fibonacci sequence? You don't. It's not so easy. It doesn't have an easy nth term. Does it even have a possible nth term? Good to research. Formula. So how on earth are we going to make one of these kind of nasty looking recursive formulas to say, well, fine, we have computers, don't we? Can't they do this for us? How can we say that a term, a sub k, is equal to the sum of its 2 previous terms? Good. A sub k minus 1 would be 1 position prior. A sub k minus 2 would be 2 positions prior. But the struggle is, for this to work, I need to actually define how many initial terms? 2. I need to say, okay, you're given starting with 1, 1. Starting with 1, 1, and then going ahead and saying, okay, now we can start at a sub 3. So this would technically just be working for k greater than or equal to 3. Dun, dun, dun. Why did I say get out your calculators? Before you leave, I want you to hit the mode button and see if there is an SEQ mode. Q for sequence. Go hit the y equals, and guess what? It's recursive. We'll talk about it tomorrow. Bye, guys. SEQ, sequence. Go to the y equals. It's recursive. Hit the x button. It's an n. Now you know what x and t and theta and n are for. Bye.